This is problem 1-10, it's on page 15. What is the weight in newtons of an object that has a mass of, and they give several masses here. Express the result to three significant figures, use an appropriate prefix. Alright, so what they've done is they've given us masses in all these cases, but how do mass and weight relate? Well, weight is equal to mass times the acceleration of gravity. Now on Earth, of course, that number we're in, looks like we'll be in metric units, so that number will be 9.81 feet, 9.81 meters per second squared rather than 32.2 feet per second squared. You got to understand the difference between the two. If you were out in space, far away from everything, where the force on your body is extremely small, you still have the same amount of mass. You'd be dead unless you had an appropriate suit or spacecraft, but you still would have no force applied to your body due to gravitational attraction. So the difference between these two, weight is something that's the result of gravitational attraction, whereas mass is just the amount of matter that makes up your body, or material. So this is the key equation, and they give us a mass in this first case of 10 kilograms. So of course we'll have to multiply that by 9.81 meters per second squared. When you do that, the math is easy, it's 98.1, and a kilogram meter per second squared is the same thing as a newton. So there we go, 98.1 newtons. In part B, they give us a mass of half a gram. We still have to multiply it by 9.81 meters per second squared to see how hard the Earth pulls down on that half a gram. So that's what we're interested in. Do the math. It's 4.905, and these are grams meters per second squared. Now, I would prefer to have newtons, so what I'll have to do is multiply by 10 to the third times 10 to the negative third. What am I doing here? Well, I'm going to make this a kilo and put it in front of the grams to make it a kilogram. And so, putting it all together, this would be about 4.91 times 10 to the negative third. We're observing significant figures, well, three significant figures, times kilograms, meters per second squared, but this is the same thing as a newton. So despite the fact that I crossed it off, I guess I'll put my box around that answer because that's the answer. Now part C, they give us, this was a decent weight. You could pick this up. This is very light. Here they're going to give us a weight that's a mass that's extremely large, and will have a very large weight. They give us, well, let's see, they give us 4.50 megagrams. We have to multiply that again by 9.81 meters per second squared. And I'll just go directly to I'll multiply this out and use scientific notation along the way. So 4.5 times 9.81 will give us 44.1. Now what I'm going to do, notice there's mega here, that is 10 to the 6th. Okay? So since it's 10 to the 6th, I'm going to leave 10 to the 3rd with this gram and make a kilogram, and take 10 to the 3rd out. So times 10 to the 3rd, that leaves me 1,000, which I can put with the kilograms, or with the grams to make kilograms. Again, these are newtons, so my answer is 44.1 times 10 to the 3rd newtons. Now I guess you'd probably be able to pick that up because a pound is, what, 4.4 newtons? So yeah, actually that's not that much. You could pick that up. Now, one more thing I could do is write this as 44.1 kilonewtons. Now, often this confuses students and they make mistakes because it takes a kilogram meter per second squared to be a newton, but a kilonewton, you got another K in there, and that K confuses students sometimes. They feel like these are the same Ks. They're not. Remember, the newton is not a gram meter per second squared. Rather, a newton is a kilogram meter per second squared. So, for whatever reason, we human beings seem to mess that up often. Try not to make that mistake.